So, welcoming you all once again to the revision course for JEE and NEET 2020, where we are seeing the past year questions, where we're seeing formulas and concepts from each chapter in physics for class 11th and 12th. Let us start off with the same. So, for today, we have two chapters, right? We have two chapters coming up. One is laws of motion, and the other is work, power, energy. Right? So, class, with regards to these two chapters, we are going to start today the actual class at 9:30. Between 9 to 9:30, there is some short assignment for all of you. So we'll keep this meeting on, right? And I'll send you all some formulas, right? Just go through the formulas, right? We'll be discussing then in 5 to 10 minutes all the formulas which are there in the chapter and some concepts in brief before we take up the questions and practice, right? So I'm putting this meeting on a short pause. So welcome back, class. Let us resume with the session. So as I told, I hope you all have taken the formulas with you, right? The formula sent to you all. Now, let us start with the class. So today we are going to cover two chapters, that is laws of motion and work power energy, right? So I would want you all to refer to the form, to the document which I've sent you all, and in that document there is a mind map, right? I'm drawing it here for a quick reference and then we'll start, right? Have a look, class. Not exactly, but some points from it. And let us do the same, but we'll join together for a short prayer and meditation before the class, like always, right? And then we'll start with the mind map for laws of motion. All right. So request you all to please join your hands, close your eyes, and let us join together in this prayer. Before we do pray, I'm remembering my gurus who have given me this knowledge with all gratitude and humbleness in my heart. Gurur Brahma, Gurur Vishnu, Gurur Devo Maheshwarai, Gurur Sakshat Parabrahma, Tasmai Shri Guruve Namah. Gurur Brahma, Gurur Vishnu, Gurur Devo Maheshwarai, Gurur Sakshat Parabrahma, Tasmai Shri Guruve Namah. Gurur Brahma, Gurur Vishnu, Gurur Devo Maheshwarai, Gurur Sakshat Parabrahma, Tasmai Shri Guruve Namah. Let us all take 3 deep breaths before we pray. A smile on the face, peace in the heart. Take a deep breath in. With the same smile, deep breath out. Once again, breathe in. And slowly, with a smile, breathe out. One more time. A big smile on the face. Peace in the heart. Let us take a deep breath in. Slowly and steadily, a deep breath out. Dear God, we thank you for such good health, wealth, and wisdom. Thank you for your love and blessings. I am thankful for all the guidance, motivation, and blessings from my friends, family, and mentors. I am thankful for such good health, wealth, and wisdom. I thank you in advance for clearing JEE 2020 and NEET 2020 in flying colors. Thank you that I've got admission into the college of my dreams in the year 2020. I thank you in advance for all the abundance and bliss of this life. With a deep breath in and deep breath out, all of us may open our eyes. Slowly and steadily. Yes. So let us begin, class. We are reading the chapter Laws of Motion. Very clear. We all have been introduced to this concept back in class 11, right? There are three laws of Newton's motion, and we'll be three laws of motion introduced by Newton, and we'll be seeing everything in a crisp, in a nutshell, before we start solving the questions, right? On this page itself. Yes, class. So I'm making certain arrows here. Just as in your sheet given, right? So it will help you to refer the sheet as I'm drawing this. And of course, please make sure that you're writing all of this in your copy, right? So here, like in your sheet, the formulas are not given. I'll be integrating the formulas on the same sheet as well, right? So please jot this down. Right now, you must have read that initially you must have been introduced to some concepts like what is force, right? So Newton's second law had defined that force is nothing but rate of change of momentum, right? This formula, dear class, has been exploited in many of the questions that have been asked in previous year's question. Although the formula looks very simple, but has a great significance when it comes to solving questions. So please jot this down. Specifically the differentiation and integration based questions, right? So force is defined as rate of change of momentum, right? Then you have this word momentum, meaning the product of mass and velocity. Substituting it here, d by dt of mv, right? Now, for this, you had two branches. First, supposing m is constant, that is the mass of the system is not changing. Then we all know, we have learned that every constant quantity comes out of the differential. Doing that, we get m times of dv by dt is equal to force. Class, remember this. Suppose you are given force as a function in time, right? In all such cases, from this equation, it becomes very easy to find out how velocity will be a function of time. Class, please remember, how velocity will be a function of time, right? Now you can also mold this equation into something else. See, have a look. You know that this a is nothing but acceleration, so you can write F is equal to ma, right? And therefore this equals to F times of m v dv by dx, right? So this implies that if you have been given force as a function in x, some value in x, then again you can integrate the same we have learnt in class and find out what is displacement in terms of x, right? Also, once we get velocity as a function of time over here, the first case which we learned, we can find out how position is changing with time. So whenever I'm writing this f of t, I mean some function in t, some dependence on t, or let's say for example v is equal to, let's say, t square plus t minus 1, etc., right? So these are some basic tricks which you will be utilizing when you're solving your questions, right? Then there is a term called impulse. There are several questions which are based on this term. I'm writing it here, impulse. You all must be knowing it by now. Impulse is basically change of momentum which has taken place in a very short interval of time. Let's say when somebody is playing cricket and the ball comes and the bat hits the ball, right? So see what was happening initially. The ball was moving towards right? So when it was coming towards the bat, it was moving towards right. So later what happens, let's say with V naught velocity, later as the bat hits the ball starts moving in the opposite direction. So the velocity or the direction of speed or direction of velocity changes. When it does, momentum changes, right? So basically final momentum minus initial momentum, right? This thing happening in very short interval of time is termed as impulse. Correct? Quick revision, please jot this down in your copies before we move ahead, right? I hope you all have written it down and see it in your formula copy also. You have this momentum delta P defined from this above equation as, have a look, integral of F dt from T1 to T2. So what does this mean? It means that whenever you have, let's say, a graph between force and time given. So let's say this is force, right? On the y-axis, on the x-axis, you have time. So I'm drawing it here. Let's say this is force and this is time. Suppose you have a graph given between the two. So whenever you have been given this graph and asked to find out impulse, how will you do it? Very simple. Calculate the area. Area of a force time graph gives you impulse. And suppose you are given with velocity, initial velocity. So you can find out initial momentum and therefore final velocity, right? So this is, let's see an example of it. Class, solve this question. This is again a very starer question, very important. Have a look in your this year's examination. You've been given that there are two axes. This is time, this is force, right? Now you have been given that the force on a body changes in this manner, right? So it is initially constant force is acting, and then it changes, right? And here you know that this entire motion is taking place for some milliseconds. Have a look. This is force given in Newton. This is time given in seconds. The first part is happening in first millisecond. In fact, this is millisecond, pardon me. This one is millisecond. This is 1 and this is 2, right? And here the force is given as 5 Newton, while here the force reaches and becomes 10 Newton, right? Now what you have to do in the question, it says the initial velocity is equal to 5 meter per second. It's given in the question, right? You have to find out the final velocity of the object if its mass is given as 2 kgs, right? How will you approach this problem? The approach will be something like this. Have a look, class. We just read that impulse is defined as the area of the FT graph, right? So you'll write here area is given as integral of FDT, right? Since it's very easy to find out the area, we need not use the integration function, right? And without using that itself, you'll get the answer, or you can move ahead, right? So this area is basically giving you impulse or change in momentum, right? Change in momentum. Do make sure you look at these units, you know. So what happens is sometimes the question seems easy, but then they'll play with the units. So make sure that you look carefully at the units. Please make sure whenever you have any graph given in your JEE or NEET exam, sometimes they might play with your uh, units, right? And therefore we have to make sure that we are not mistaking over here despite knowing everything, right? So yeah, I'm sure you all will be very careful over seeing the units, right? Now we'll write change in momentum is given as final momentum minus initial momentum, correct? Which can be written as m times the final velocity minus initial velocity, right? Now find out the area. See, we have one rectangle and the other is a trapezium. So we have area. I'll calculate it over here. Area is given as, so for the rectangle, this will be the area. This is 1, right? While this is 5, length and breadth. So you have area of the rectangle is 5 plus the area of trapezium. It's given as half into sum of parallel sides. Sum of parallel sides is 5. This one is 5, right? And this one is 10. So half into sum of parallel sides into distance between them, right? So the distance between them is 1 again. Remember the units. The units are Newton milliseconds, right? Newton milliseconds. So you'll write this 5 plus 15 by 2 Newton milliseconds, right? That is 5 plus 7.5 or 12.5. Now, now if you want to convert it in terms of Newton seconds, all you have to do is multiply it by 10 power minus 3. I hope you all are very well aware with the prefixes like milli, macro, micro, etc. Right? Giga, nano. So you have this as Newton seconds. Now this is representing the change in momentum, right? Because this is the area. So it is delta P, or change in momentum given as delta P and equal to 12.5 into 10 power minus 3 Newton seconds. So please jot this down, class, and try calculating velocity now. I've given you the hint. I've given you almost everything that could have been shared. So yeah. Try finding the velocity now and let me know your answer as your answer comes. Please raise your hand once your answer comes. Everything is there on the board, class. You need to find out what is the final velocity, VF or UF. Yeah, this VF. Let me know what it comes. Yes. And raise your hand once you get the answer, class. This will actually make it clear for me if you're understanding. Yes, class, go ahead. Raise your hand as you get the answer, the value of final velocity. All right. So I can see that there are 5 hand raises. Okay. Harsh, Mahila, Monica, and Shri are yet doing it. Okay, no worries. Yeah. Class, have a look. So, okay, now I think 2 more have done. Yeah, no worries, no worries. Have a look, class, here. So we have change in momentum. I think 8 are done. Great. Class, have a look. Change in momentum is, we just read, final momentum minus initial momentum, which can be written as mass times of final velocity minus initial velocity. We have got this as 12.5, right, into 10 to the power minus 3. You know, we have been given mass as 2 kg. So we can write this here as 2 into 10 power 3, oh sorry, 2 kg given by final velocity minus 5, correct? So we have 12.5 into 10 power minus 3 divided by 2, and ultimately we get the answer, right? So this is basically 5 plus 0.00625, you know. So we have a very small change in velocity. Initially it was 5, now it's 5.00625. A little out of the box questions, but yes, such questions can be asked in your examination, right? At least 1 or 2 questions are there in your paper which have a little challenging calculation, just to check the patience and presence of mind of the students. So I hope everyone is clear. So class, whoever is uh, not clear, please raise your hand. Rest may put it down. Yes. Okay. Okay. All right. Great. So let's move to the next concept then, if all are clear. The next concept that you all need to understand for this chapter is the concept of equilibrium. I'm writing it here, the concept of equilibrium. You know, several questions are asked on this concept almost every year, and another one is friction, right? Another one is friction. So telling you all what friction is. Now, please jot this down. Some students still have several minor confusions involved in this topic. So let us clear it now itself, right? So the concept says, what is friction? Friction is a force that opposes relative motion relative motion between two surfaces, right? Between two surfaces, the force that opposes relative motion between two surfaces, and what else? It is the component of, it is the component of contact force, contact force parallel to the surfaces. So telling you all in a gist, in a brief, about how does friction, concept of friction holds. So you'll have several questions in the examinations which are based on this concept, right? A very important concept. Almost every year you get concept based on friction or questions based on friction, right? So let's say there is a body here on a surface, right? Now, whenever a body is kept on the surface, I hope you all are aware with the concept of free body diagram. That is, we see that how many forces are acting and in which direction, right? So let's say the first force is the weight of the object, the weight of the object. let's say it is acting downwards and it's equal to mg, right? Because of this weight, the surface is applying a normal reaction. I hope you all are aware, normal reaction. So normal reaction, I'm showing it here, by the surface on the object, right? So from over here, right? Now you can either show it along the line joining the center of mass of the body, or anywhere along the surface, because normal reaction is acting at every point of the surface, right? Now let's say this is the center, right, through which we are representing normal reaction, right, n, and the weight. So this is the condition when a body is just kept on a table. Now what happens is, I you come here, you stand here, right, and you want to pull this object. So you take a rope in your hand, let's say this blue color rope, and you start pulling it, right? You start pulling it. So now when you start pulling it, you're actually applying a force on it. You're actually applying a force on it. So when you're applying a force, let me now remove this line and rather put a line representing the force. Let's say this is the force F. So by the application of this force, what happens? Suppose the surface has something called as coefficient of friction. Coefficient of friction. So because of this coefficient of friction and because of some unevenness at minute scale over here, the surface will not want the block to move away from it, right? I'll repeat. The surface will not want this block to move away from it and will try to prevent, the surface will try to prevent relative motion. Please remember, relative motion, not just motion. Relative, there is a difference between relative motion and motion. Relative motion. So the surface will try to prevent the relative motion, and therefore it will, in order to oppose this relative motion, it will apply some force which is in the direction opposite to the direction in which the body is tending to move. Class, remember, right now the body has not started moving. The body is trying to move. So I'll write it here clearly. Have a look. Please jot this down again as a note, that the surface tries to prevent the relative motion, right? And what it does is, the tendency of relative motion is prevented using, the tendency of relative motion is prevented using frictional force, right? Now we have understood, let's say that frictional force is F. So what happens is, until the time the body is not moving, we call this force as static friction, right? So friction acting on the body, right? Acting on the body until the time there is no motion. First is when there is no motion, is called as static friction. Now suppose what happens is, I see that the body is not able to move. So I take a decision. What is my decision? My decision is that I'll increase the force. I'll pull the body with even a larger amount of force. So the surface and these mutual surfaces are actually also very much arrogant. They'll say, okay, if you will increase this force, we'll also increase the friction, right? They'll also increase the friction, and they'll still prevent the body from moving. So what does this imply? This implies that this static friction we are talking about is a variable and self-adjustable force. Variable and self-adjustable force. Write it down. Self-adjustable. So what happens is whenever you're trying to pull the body, the force is increasing, this F is increasing, and therefore friction is also increasing. But will it keep happening until infinity time? No. The answer is absolute no. After some time, the surface and the body will allow to let go. They will say, this is my maximum value of friction beyond which I cannot afford to keep this body in a static position. In a static position with respect to the surface. Important. I'll write this here. So, please jot this down. As F increases, small f also increases, but F becomes maximum at a certain value, that is friction becomes maximum at a certain value and cannot increase beyond that, and cannot increase beyond that. Please jot it down. Cannot increase beyond that. And finally, what will happen? Finally, what will happen is, until now, when the man was trying to pull the block and the surface was trying to keep the block over here only, there was an equilibrium. There was an equilibrium. But as soon as the friction, but as soon as the friction becomes maximum and stops increasing, but the force of pulling the block keeps on increasing, the equilibrium will no longer exist, or it will break. What will happen? Now the object will start moving. The object will start moving in the forward direction because the net force is now making it get pulled over here. See? So this is the condition. This is the free body diagram. Between the surface and the block, a friction is acting backwards at its maximum value. A force is acting on the block in the forward direction. There is a normal reaction acting on the system in the upward direction. And there is a weight which is acting in the downward direction. So this is normal reaction, and normal reaction is because of this weight acting in the downward direction along the center. Class, please mark, I'm talking about the center. We'll be seeing this tomorrow when we are considering, tomorrow when we are considering rotational motion, then we are going to talk more about it. So here a force is acting downwards, which is weight. Now have a look. So now this friction which is acting, which is maximum, right? So at this position, at F is equal to F max, we have absolute equilibrium. After this, there are no chances of equilibrium, and this is called as threshold condition, right? At this position, this is the maximum value of friction which can be equal to the regularly increasing force, capital F, right? And at this position, this is how the horizontal equilibrium is existing. Of course, in y direction equilibrium is there because net force in the upward direction, normal reaction, is equal to the net force in the downward direction, which is equal to weight or mg, right? This is the condition. After some time, what will happen? So see, I have written here in the first case that when there is no motion, then this friction is called static friction, right? Now this is that threshold condition of no motion or static friction. Second part is called as kinetic friction. Kinetic friction. So now what happens is kinetic friction value is a little lower, not very much, but a little lower than the maximum value of static friction. I will repeat. I'll show it here in the form of a graph, right? So have a look here, class. This is what was happening. So I'm plotting a graph between what? Between the force which the person was applying. See, you were applying this force, right? F. So this F and the friction which the relative surfaces were applying on each other, right? See, I am using the word relative surfaces were applying on each other. So basically, when I'm saying that the surface is applying a force F on the block, actually, if I draw a free body diagram for the surface, a force of friction is also acting on the surface in the opposite direction, which is again a repercussion of Newton's third law of motion, right? So see, when we are discussing all of this, right, when we are discussing all of this, impulse, right, or when we are talking about equilibrium, we are actually slowly moving from the concept of inertia to the second law. The first law talks about inertia. Second law talks about F is equal to ma, right, or rate of change of momentum is equal to force. Then the third law talks about that every action is an equal and opposite reaction. So this is what we have come to here. So now force starts acting, which is called as kinetic friction. This is what it looks like. So initially I was increasing F, and that is the applied force. This is the applied force, right? Whereas this is friction. And this friction was also increasing, but only till a certain limit, after which it drops down by a small value, right? A small hump develops here, and then there is a stagnant value of friction, right? So this maximum value of static friction, this is the maximum value of static friction called as F max, right? Whereas this entire range is static friction. This is the time until which the body is not moving. This is the range of static friction, right? Whereas this constant or stagnant value, let me draw it with blue maybe, right? This one. This one is called as kinetic friction. It is a little lower than the maximum value of static friction. So this is called as this pink one. I'm trying to match it with the pink here. This is kinetic friction. Well, the upper one is maximum static friction. So I'll write it by FK rather. FK, right? So this is telling you the kinetic friction, whereas this peak is telling you about maximum static friction. I hope the concept is clearly setting in all your minds, right? Now this kinetic friction and static friction, how are they given as? So basically, there is no formula for static friction. Class, remember, there is no formula for static friction. Why? Because this static friction is actually an arrogant force or a self-adjustable force which becomes equal to the F. That is, as much force I apply, that much is the value of static friction. See here, this line. See here, this line. This line is basically F is equal to F. See here, I'm writing something, the equation of this line. The equation of this line is y is equal to x. Y is equal to x means small f is equal to capital F. That means as much is the value of applied force, so much is the value of static friction. Very important. The static friction is a self-adjustable force, but it also has a maximum value, right? And that maximum value is given as normal reaction into the coefficient of friction, mu n, right? Now, this, now let us establish the relation. So we'll get this class mark. This is the only holds for threshold condition, right? This only holds for the threshold condition. So we will write F is equal to mu into N, and we know that N is equal to mg. Therefore, maximum friction, this is just for F max, maximum static friction is equal to mu mg. Maximum static friction is equal to mu mg, right? Now we have understood the entire funda of how static friction works. Now the same does not hold true for kinetic friction. See here, the kinetic friction is a constant quantity, right? Whereas we can see here, the static friction is a variable quantity. It's varying. It's varying. As much is the applied force, so much will be the static friction, only till a certain point of time, right? So kinetic friction is a kinetic friction is a constant quantity and given as Fk is equal to mu k into normal reaction, right? If there is no motion taking place, accelerated motion taking place in the vertical direction, so we can say that in the vertical direction there is equilibrium. So we can write again mu k times of mg is the value of kinetic friction. It is static or it is non-variable or constant. Whereas the value of static friction was varying. And why is it called static? Because the bodies move, because the body is not able to move. Whereas here, why is it called kinetic? Because the body is moving. Here body moves, right? Whereas over here, for this one, the body is not moving. For static friction, right? This is for static friction. So class, as you have written all of this down, please raise your hand so that I can move to the next page. Yes. Just give me a minute. Now we'll take a past year question on this concept to make the matters clear. Yes. Once you're done writing all of this, please raise your hand. Yes, class. Okay, so I can see that some of you have raised hands. Okay, I think all of you. Shri, can you raise your hand or maybe give a signal by thumbs up or something like that, so that this will help me understand that you're done writing. Yes, Shri. Okay. All right. Thank you. Class, so now, thank you everyone. You can bring your hands down. Before we see a question, there is one more concept which is called as common forces. So here you have understood the funda of equilibrium. In equilibrium, the net force may be zero. Equilibrium can be separate. It is called as, it may be there in the y direction, it may be there in the x direction, right? Now, again, something important is free body diagrams, which we just saw right now, and we also have read about friction, right? We'll be seeing something more, but before that, there is something called as some common forces. Some common forces, right? Like, note them down: weight, normal reaction, right? Normal reaction. Then you have tension and spring force. You know, these are some forces which are so intriguing that sometimes if you know the concept well, are you able to make questions based on that. So I'm taking a small section where I'm just giving you tricks of how to solve questions based on these concepts. So I'm writing here, this concept is so important. I'm writing here common forces. So class, look, we have first kind of common force is weight. We have just seen weight is just the force which always acts in the downward direction, in the direction of gravity, and given as product of mass and acceleration due to gravity. We are clear. Now, there is a force called as tension. Some students require a very clear understanding of what tension is. So let's say I have a block, okay, and let's say I have a string attached to it, okay. Now tell me one thing, what if I want to pull the block with this string? I can, right? I can. So when I want to pull using a string, this is a string or a rope using which I'm trying to pull. Possible? Possible. But what if I want to push the block with a string? Is it possible? Try to think about it. If I want to, I'll repeat my question. If I want to push the block with a rope or a string, is it even possible? No, right? It is not possible to push a block with a string or a rope, which means that the force which is developing over here, which is helping you pull the block, is nothing but tension, and this tension is a pulling force. Remember, this tension is a pulling force. So forces are basically of two kinds on this funda, on this basis. One is pulling and the other category is pushing force. So pulling means they'll tend to, I'll just show how, right? I will just see about it. Now, another one is normal reaction. Normal reaction. So see, normal reaction is always one thing, it is always perpendicular to the surface, very important, right? Second one is that it is a pushing force. It's a pushing force. So all I mean to say is that if suppose you have, I'll give you an example of this. Suppose you have a wall, right? You keep a block here. So now if you try to push the block on the wall, right, by say, let's say force F, then the wall will also try to push you by a force called N, which is normal reaction, right? Normal reaction. This will be the force applied by the wall perpendicular to it on the block, by the wall on the block, remember, right? Now let's say if this block is just kept, it is just kept, nothing else, on a surface which is horizontal. So the weight will act downwards on the block and the surface will apply a force on the block in the upward direction, which is again perpendicular to the surface. Another example, if you have an inclined surface, right, now what will happen? Here you keep the block, again the surface will apply a normal reaction, but this time the normal reaction will be perpendicular to the surface, whereas the weight will still be acting in the downward direction, right? In the downward direction. I hope you all have very well read this, that this weight is can now be split into two components. One will be perpendicular to the direction of the inclined plane and one can be along the direction of inclined plane, right? It will depend upon the angle theta, right? This angle, we'll see a question just now, right? This will be the component along the direction of the inclined plane will be W sine theta, right? And the component, so all you can do is just draw horizontal line here. This is theta, so this is also theta. So this one the perpendicular component will be equal to W cos theta, W cos theta, whereas this parallel component will be W sin theta. I'll draw it here in a bigger fashion for better understanding. This is the inclined surface, right? Here we have a force acting, here a block is kept, right? A block is kept, its weight is acting downwards, W, right? This angle of the inclined plane is theta, right? Now all I do is draw this normal to the surface and this horizontal as well as the vertical line. See here, this is the vertical line. So this angle is theta, this is also theta, right? Corresponding angles. And since this is normal, this entire is 90. So this angle will become 90 minus theta, right? And therefore this also becomes theta. Now that this angle is theta, we have this one. See here, I'm drawing an arrow. This arrow is in the direction perpendicular to the inclined plane. Remember, perpendicular to the inclined plane. And this is called as W cos theta. Whereas this component of weight, actually I should not directly write such a big arrow because I've shown weight as here. So I'll basically draw the components in this manner, right? So here is how your weights are acting. So this weight or this green color arrow is talking about the component which is parallel to the plane or W sine theta, whereas this component which is perpendicular to the plane is W cos theta, right? I hope everyone is clear with this concept. Please jot this down, and once you are done, let me know by raising your hand so that we can move with the questions. Yes. One last force along with this, in case you have jotted this down, is a very special force called as spring force. Spring force, right? So how does spring force work? Class, look here. Suppose you have a surface, a vertical surface or a wall, right? A wall. What you do is you put a spring on it this way, right? And you start pulling this spring towards you. You're standing here, right? And you start pulling the spring towards you. What will happen in the spring? In the spring, if I draw a free body diagram of the spring, so this is what it happens. The spring gets pulled by you, right? Pulled by you in the rightward direction. So force F acts on the spring in the rightward direction. But when you are doing this, the spring is also trying to pull the wall towards itself, right? So the spring is trying to pull the wall towards itself. Class, remember, this is an ideal spring. This is an ideal spring. Generally, in all your questions, you all are given that the spring is massless. Mark that whenever there is a massless body, it will carry forward the same force you are giving to it to the other object. So let's say this is the spring, right? Here is the wall and here are you. So what happens is you bring a force or you apply a force on the spring F. Similar force will be applied by the spring on the wall. Class, I'm repeating, by the spring on the wall in the rightward direction. That is, the wall is pulled towards right. So according to Newton's third law of motion, this spring is also pulled by the wall with the equal and opposite force F. This is the key. So all I'm trying to say is, see, listen here clearly. This spring will have two forces acting on it. Only one is consciously applied. That is, this force F is by the man, right, on the spring down in the rightward direction, whereas this green force is actually applied by the wall. Although it will not be shown in most of your questions, but it still exists. This is what you have to remember, right? Also, similar case develops over here. See, when I'm talking about tension, class, have a look here. The same example where man is pulling the block, right? So we understood one aspect of it, that when you apply tension via a rope, there will be a force of T acting on the block in the rightward direction. How about the man? How about the man? When the man is trying to pull the block towards itself, the rope is also trying to pull the man towards right. The rope is also trying to pull the man towards right, this way, with the same tension T. With the same tension T. Why are we using this pulling word? Because tension is a pulling force. What kind of force is tension? Tension is a pulling force. We'll see some examples which will make matters clear, right? Let's see the examples one by one. Yes. So these are questions from some past years, right? And I hope this will make the matters clear. So have a look, everyone. Write this first question. You have been given in the question that yes, class, you have been given in the question that you have an inclined plane given as this way. This is question from JEE 2014. You have an inclined plane given as this manner, in this manner, right? So these questions become highly imperative when we talk about your NEET examination, because if this question has appeared here, it might appear in your NEET exam this year or maybe next, right? So please have a look that you have a block kept over here. A block, I'll draw it by myself. A block is kept over here on the surface, right? A block is kept on the surface. Now you're being told that a block of mass M is placed on the surface with vertical cross section given as y is equal to x cubed by 6. And the coefficient of friction here is given as 0.5. It is given as 0.5, right? This point, or maybe this line, the equation of this line is given as y is equal to x cubed by 6. So basically all I mean is that when you draw a line here, so basically they have represented this on an xy diagram. So this is y axis, right? And here is the x axis. This is what they have shown. Now they are saying that for a given particular point, let's say this one, let's say this point, if this is the value of y, right, and this is the value of x, the x and y depend on each other by this relation. This is what they have told in the question, correct? Where vertical is y axis, horizontal is x axis. They are saying that the maximum height above the ground where the block can stay without slipping, maximum height above the ground where block can stay without slipping. without slipping. Class, when does slipping take place? Slipping means that even despite friction, the block starts moving downwards. That means we have to take that threshold condition for which the block will remain in equilibrium. For which the block will remain in equilibrium, right? The threshold condition for which the block will remain in equilibrium will happen when, so I'm drawing the free body diagram, have a look everyone, will happen when, have a look everyone, on this block there is weight acting, which we just learned, W sine theta downwards, right? Normal reaction is acting perpendicular to the surface N. Here friction is acting in this direction, right? And it is trying to prevent the block from moving downwards, correct? You're being asked that what is the maximum height, that is the value of y equal to y max. This is what you're being asked for no slipping, for no slipping, right? So now for no slipping, we will have this F. This F should be equal to W sine theta. That is, there needs to be an equilibrium along, I'm writing here something, there has to be an equilibrium along the plane, along the inclined plane, or along the incline. Along the incline, there has to be an equilibrium for no slipping to take place. This is the meaning of no slipping, right? So have a look, class. What we'll do, we know, we have just learned that this F is nothing but mu into N, right? And this W we'll carry it forward. So we'll get mu times of mg is equal to mg, and wait a minute, so we'll have, just a minute. Now what about N? This N will actually be equal to mg cos theta. See here, or W cos theta. Since we have written it W here, I'll write it in the form of W only. W cos theta. See here everyone, we'll have two expressions. One will be N is equal to W cos theta. This is talking about the equilibrium perpendicular to the plane. See, first of all, forget all equilibrium. Just concentrate on the forces. So we have one force, normal reaction, right? Another force was weight, which we have already resolved into components. And the next one is friction, right? So this friction is now at its maximum value. This friction is now at its maximum value, right? This maximum value of friction is trying to make sure that the block does not slip. Class, I'll write here, the F max is trying to make sure that block does not slip, right? So what it does is it makes itself equal to W sine, W cos, sorry, I'll rub this, yeah, right? So we have seen that it makes itself, already we have written it, equal to W sine theta, right? That is equal and opposite forces, and N is already equal to W cos theta, that is the normal reaction, because of the equation of equilibrium along incline, right? Equilibrium along incline. Net force 0, sorry, perpendicular to incline. Equilibrium perpendicular to incline. So in the direction of equilibrium, in the direction perpendicular to the incline, there is equilibrium. Therefore, we get N is equal to W cos theta or mg cos theta. Write it over here, mg cos theta. Here you have mg sin theta. W is mg, right? Mg and mg gets cancelled on both sides. You get mu is equal to tan theta, right? Class, this is also a standard result you all may remember, that at the position of limiting equilibrium. So basically this condition is also called as limiting friction. The maximum friction I've drawn here, no? This one, F max. This is also called as limiting friction, or this maximum static friction is also called as limiting friction. You all may note it down with U. So see what is happening here. This mu is equal to tan theta. What is theta? Theta is the angle which the line is making with horizontal, correct? And we know the equation of the line. It is y is equal to x cubed by 6, correct? Theta is angle made by incline with horizontal, correct? With horizontal. So what you're going to do, yesterday we had just read that whenever you are given with an equation y is equal to say x cube plus x plus 1, how do you find out tan theta? Of course, we know that dy by d theta or slope is nothing but tan theta. So calculate the slope in order to proceed ahead if this was the equation, right? Now, what about in our case? In our case, we have been given that y is equal to, we have been given, see here in the question, y is equal to x cubed by tan theta. So just differentiate it. What do we get? Dy by dx is equal to 3x square by 6, giving you x square by 2, right? And this is nothing but tan theta, right? Tan theta. In the question, it is given mu is equal to 0.5. Substitute it here. 0.5 is half. We'll have tan theta is equal to half, right? And we just got that tan theta is also equal to, from here, see here, tan theta is also equal to x square by 2. Have a look, everyone. Tan theta is also equal to x square by 2, right? This gives you x is equal to plus minus 1, right? X is equal to plus minus 1. I'll repeat what I've done, but before that, just have a look over here, right? X is equal to plus minus 1. Now, for this value of x, you need to find out what is the value of y. As simple as that. So we'll substitute it in the equation. Y is equal to x cubed by 6. This gives us 1 by 6. So 1 by 6 meters is the maximum value of y for which the block can remain steady without slipping. Class, I'll repeat what I've done. We have found out equilibrium along the incline and perpendicular to the incline. So for the equilibrium along the incline, this maximum force, have a look here. I'm repeating in a short go. So we have this maximum friction is equal to W sine theta because of equilibrium along the incline, right? And because of equilibrium perpendicular to the incline, we have normal reaction is equal to W cos theta. So this gives us mu is equal to tan theta. Now, how did tan theta come? We remembered that tan theta is nothing but slope or m or dy by dx. So we had the value of y, we differentiated it in order to get x square by 2, and this was nothing but tan theta, right? It was given in the question the value of mu is 0.5, substituted 0.5 here, and then instead of tan theta we substituted x square by 2 to get x value as plus minus 1. This gives us the value of y, right? Minus 1 is of no meaning, right? Because we are talking about above the ground, so y has to be positive, and therefore we get the value of positive value of y as 1 by 6 meters, right? So 1 by 6 meters is the value of y for which the block will remain steady. If you try to pull the block above that, it will start slipping and come down, right? Now, class, have a look at the question, try to absorb it, and you can ask your queries. Yes, class. Class, everybody who is clear with the concept that we have used here and the question working, please raise your hand. If you are clear, please raise your hand. Yes. Okay, great. So let's move to the next one. Thank you, class. You can bring your hands down. We'll take the next question, right? So the next question says, it's again a question from the year right? This is a question based on collisions, or we instead, before we start collision, we'll take some other topics for you also. We'll take some more questions on this for better practice. Okay. So now, okay, class, write this down. This is question from JEE 2017, right? The question says that there is a body of mass m is equal to 10 power minus 2 kg, right? You're being given that it experiences a frictional force F given as minus kv square. Okay, it's a variable force depending upon the velocity. You are given that the initial speed u naught or v naught as 10 meter per second. It says that after 10 seconds, its energy is equal to half, pardon me, this is 1 by 8 m v naught square. Energy is equal to 1 by 8 m v naught square. You have been asked what is k, this k. Question from 2017 NEET JEE exam, and this question is actually a probable question for this year's NEET. Try solving. We just did something very similar to it in the first page. See here, everyone, this one. Recalling everyone these equations where we have a relation between force and velocity, you'll have to apply things of this sort. So try recalling this concept and applying it over here. Yes, quick class. Right? What do? We know that, all of us know that F is equal to ma, right? So let's write frictional force acting is equal to m into a. Given this, given as minus k v square. What next? So what next, right? We can just write this as dv by dt, right? Because we are being talked about time. Class, remember, I told you all, we always have, for variable acceleration cases or general cases, we have two ways of representing acceleration. One is dv by dt and the other is dv by dx. So see here, there is no mention of position, right? Whereas there is a mention of time. That is why I'm choosing this formula, a is equal to dv by dt over here. So we'll write m times dv dt is equal to minus kv square, right? What will this do? This will establish a relation. Doing this will establish a relation between velocity and time, right? Once I get that, I'll be very easily able to find out how velocity is varying with time after 10 seconds and thereby calculate kinetic energy, etc. Right? Let's do it. So we'll have, let us group similar variables together. We'll have dv upon v square is equal to minus k by m dt, right? Group similar variables together. Now take an integral on both sides, right? Let us do it for general value. We have been given that in the question that at time t is equal to 0. See here, initial velocity. So whenever initial word is given, you have to interpret it as t is equal to 0. So you have been given at t is equal to 0. What is the velocity? See here, 10. 10, correct? Now, and you have been also told that we have to find out a general condition first. So let's do that. Let's find out a general condition. Integral of 10 power v power minus 2 will be v power minus 2 plus 1 upon minus 2 plus 1. We have read this formula, right? We'll integrate it from 10 to v, and similarly on the other side minus k by m are constants. They will come out of the integral, and we will have integral of 1 which is equal to t integrated from 0 to t, correct? So this will yield us minus 1 on the other side, 1 by v from 10 to v here, minus k by m t from 0 to t. Expand it, you will get minus 1 cancelled on both sides. You'll have 1 by v minus 1 by t 10 is equal to t into k by m, right? Correct? So this should give you 1 by v is equal to, on the other side you will have 1 by 10, right, plus kt by m, correct? Right? Now we can write v is equal to 1 upon, instead of writing 1 by 10 I'm using 0.1, right, times of kt upon m. So this entire expression, see what was our purpose? Keep the purpose in mind and things will always be clear for you. We had a purpose. The purpose was we wanted to find out a relationship between velocity and time, and we are so much successful in that. We now have a relationship between velocity and time, 0.1, 1 upon 0.1 plus kt by m, right? Now we are told that, see the question here, initially the velocity is this, after 10 seconds instead of giving velocity they have given kinetic energy, right? So we know that kinetic energy is equal to, initially, or we have been given kinetic energy at t is equal to 10 seconds. How will we write? Half mv square, correct? So let us find out what will be the velocity at t is equal to 10 seconds. So we'll substitute it here to get the kinetic energy. So at t is equal to 10 seconds, velocity is equal to 1 by 0.1 plus value of k we don't know, time is 10, right? And mass is given in the question. See here, right? 10 power minus 2. So right here mass as 10 power minus 2, correct? So this will give us velocity is equal to 0.1 plus 1000 k, correct? This is the value of velocity in terms of k. Substitute it over here. We know the kinetic energy. See here, kinetic energy is 1 by 8 m v naught square, correct? 1 by 8 m v naught square, and v naught is 10, correct? So we have half m v square. Instead of v square we will write this expression, right? We'll have it as 0.1 plus 1000 k, correct, whole square. And we also have this expression is given in the question. See here everyone, we have been given that kinetic energy is 1 by 8 mv naught square. So I'll write here 1 by 8 m v naught square, correct? When you expand this, instead of v naught you're going to put, right, you're going to put v naught is equal to, see here 10, it's given initial velocity. So we'll put 10 square is equal to, and this will become 4, correct? So 10 square upon 2 whole square is equal to 1 by 0.1 plus 1000 k whole square. See, have a look class. What I've done, instead of 4 I've written 2 square. This was 10. So this is 10 square by 2 square, and here you have 1 upon 1 plus 0.1 plus 1000 k whole square, correct? This will yield you 5 is equal to 1 upon 0.1 plus 1000 k, correct? You need to find out what is k. Very simple. Bring it over here. On the numerator side, 1000 k plus 0.1 is equal to 1 by 5. 1 by 5 is 0.2. So you have 1000 k is equal to 0.2 minus 0.1, which is equal to 0.1. And therefore, k value comes out to be 10 power minus 4. simple algebra to reach the answer. All that we had to do is to equate the expression of kinetic energy given over here to our expression of kinetic energy, which we obtained by getting the velocity at time t is equal to 10 seconds. Class, if the concept and the question are clear, please raise your hand. Yes. Right? Okay. So I can see that there are still some left. Class, please keep your hand raised. I'm just seeing if there are any one of you who are yet to ask. Okay, everyone is done. Right. Thank you, class. You can bring your hands down. Yes. So class, one more question. This time, this question is based on the concept of impulse we just read, right? It's an AIEEE question from 2010. Have a look. The question says that there is a position time graph given of a one-dimensional motion of a body such that the mass is 0.4 kgs. Okay, the mass is 0.4 kgs. You have to find out the magnitude of each impulse. That is magnitude of each impulse, something like this. So see what's happening. This is the graph. The position is increasing, right, and then decreasing. Again, it's increasing and then decreasing linearly, right? All these are symmetrical. So now we have this one, highest distance traveled is 2 meters, right? And this y-axis is representing time. So every half triangle is being made in 2 seconds and a full triangle in 4 seconds. So this is 4, this is 6, this is 8, right? This one is 10, this one is 12, and so on, right? You're being asked what is the magnitude of impulse, right? You have different options in the questions, but let us see how will we find it out. Class, recall, how did we write impulse as? Impulse is nothing but change in momentum, correct? Given as final momentum minus initial momentum, correct? Now, what is the value of final momentum and what is the value of initial momentum? So here in the question, they have actually given you even one more curve. So I'll draw one more curve here, this one. In fact, the last triangle, it goes on till 16 such that it attains its apex in t is equal to 14 seconds, right? This is in seconds. Now you have to find out the change in momentum. Class, we have read, I have given you all a graph or a table which says that the slope of an xt graph, mxt, is nothing but velocity, right? So here, see what is the initial and final velocity. See here, the initial velocity, that is this one, is the slope of this line. What is the slope line? Slope line is delta y by delta x, right? So what is delta y? This is delta y, correct? While this one is delta x. See, the value is 2 by 2, right? That is 1 meter per second, correct? So we'll have initial velocity u is equal to 1 meter per second. Have a look at this one. Here, the initial velocity or the final velocity, so this was u, the one which we just drew. This was u, right? Now what about the final velocity? Final velocity is also delta y by delta x. See, this is delta y and this is delta x, right? Or you can write delta x by delta t, whatever. So we'll have v here as delta y by delta x or delta x by delta t, right? Given as 2 by 2 again, right? But remember, this is a falling line, right? This is a falling line, if you all can recall. Whereas this one, the first line is a rising line. So its slope is positive. Whereas this line will have a negative slope. So it's minus 1 meter per second. So the final value of velocity is minus 1 meter per second. Correct? How will you solve the question? You'll write final momentum PF is equal to m times of final velocity, right? And P initial is equal to m times of initial velocity. Substitute it over here. Take m common. Final velocity is minus 1 minus of initial velocity minus 1, right? So you will have, and the mass is given as 0.4. So you'll have 0.4 into minus 2, right? That is equal to minus 8 by 10 Newton seconds. Or you can also write it as minus 0.8 Newton seconds. Class, is this clear? You had a graph between x and t. Using the graph between x and t, we calculated velocity, initial and final, right? Substituted in the formula for impulse and got the answer. This is the impulse in the given motion, right? Correct? Suppose if I ask you what is the average force acting, then what you'll do? You'll just divide impulse upon change in time. Impulse upon change in time. Average force for this entire aspect, and you'll get the force, right? Correct? So I hope the concept is clear. If it is, please raise your hands. Yes, class. This is again the concept based on impulse, the concept which we just read in the beginning of the class. All right. Thank you, class. You can bring your hands down. Let's go to the next question. Now, class, we are slowly progressing to the chapter work, power, and energy, right? This work, power, energy has basically just 2 or 3 concepts which are very crucial to your understanding and will help you all a lot when solving the questions. So, the first one. So I'm writing down the important concepts from the chapter law, work, power, and energy, from which the questions are asked every year, right? Work, power, and energy, right? So from this chapter, something which is very important, always you all should remember, is the definition of work. Simple. Work is defined as the dot product of force and displacement when F dot X, or if I denote it by S, displacement, when the force is constant. When force is constant. That constant means, again, it is not varying with time. So it is F dot S, right? Second definition, which it becomes important, is work is equal to integration of F dx when force is varying. When force is varying. 2 important points to keep in mind. Quickly jot it down. Right? It's a variable force or a varying force. Then there is the principle of conservative force. From the application point of view, conservative means something should be conserved when a conservative force is acting on the body, and that thing which is conserved is nothing but mechanical energy. Class, remember, mechanical energy is conserved whenever a conservative force is acting. What is mechanical energy? Mechanical energy is conserved. Conserved means it remains constant. I'll repeat, when a conservative force acts on a body, its mechanical energy remains constant. right? Its mechanical energy remains constant. So mechanical energy comprises of two parts. One is kinetic, the other is potential energy. I hope you all are aware with this concept, right? For this particular chapter, all you should remember is that potential energy is given with respect to a surface, right? Suppose this is the surface, so the potential energy above the surface will be equal to, at a point which is x meters above it, will be mgx. We'll consider g is the acceleration due to gravity and m is the mass of the body for which you are calculating energy. Suppose if you're calculating the energy below that surface, we'll take u as minus mgx if it is at x meters below the surface. Very simple, right? We all know, very simple, kinetic energy is nothing but half mv square, right? This is another important concept in the chapter. Next one, which is important, is to understand the concept of work energy theorem. Work energy theorem. I hope you all must be remembering it, that whatever kind of work, class, some students confuse it with just conservative forces. No, whether conservative or non-conservative forces, whatever act, this total work done by them is equal to change in the kinetic energy. As simple as this. Jot it down. Change in the kinetic energy is equal to the total work done on a particle or an object, right? Or you can also write this as the final kinetic energy of the body will be equal to the work done, total work done on the body plus its initial kinetic energy. So this is how you denote or express work energy theorem, right? Now something very important from this previous concept which we just learned, for whenever conservative forces are acting on the body, you can write, since mechanical energies remains constant, that means initial potential energy plus initial kinetic energy will be equal to final potential energy plus final kinetic energy. Class, I repeat, whenever conservative force is acting on a body, initial kinetic and initial potential will be equal to final kinetic and final potential. One of the very common examples of a conservative force is gravity. So whenever an object is moving under gravity, suppose a ball starts falling, right? So it initially, if it is falling from a height of, let's say, h, so its energy, which energy? Potential energy will be mgh. Suppose its initial velocity is u, so we'll have half mu square as its kinetic energy. Now suppose it reaches another height which is capital H, or let's say it was capital H earlier, now it becomes H. So now its energy will be small mgh, potential energy, and its kinetic energy will be half mv square if v is its velocity. So we will write half m u square, initial kinetic energy, plus initial potential energy mg capital H will be equal to half m small v square, right, plus mgh, right? I hope it's clear with everyone. Initial height capital H, small height, later height small h, initial velocity u, final velocity v. So this is how whenever an object is falling under gravity, right, its energy is conserved in this manner, because what force is acting? Gravitational force, which is conservative in nature. Another important part, generally this is how books define, that whenever conservative force acts, it is independent of the direction of motion or the path of motion. So this is path independent. You all can write this also. So this basically means if I take the body towards right and then make it fall, it would make no difference if I make it fall directly, right? This equation and this equation will still remain the same. So it's path independent. I hope everyone has jotted this down. another super duper important concept which comes into play is collision, right? Again, you will have collision of two types, elastic and inelastic. Telling you all directly what is the technique to solve such questions before we take up some questions and solve. For elastic collisions, remember, both are conserved momentum, that is P, as well as kinetic energy E, or I'll write it at Ke as Ke. Both, so conserved means constant. Net momentum and net kinetic energy both will remain constant for a elastic collision, whereas for an inelastic collision, only momentum remains conserved. So when I'm saying momentum remains conserved, I mean the momentum of the system remains constant. Initial value plus final value, right? Net initial value is equal to the net final value. This will always happen whenever a collision is happening. Class, remember, total momentum will be conserved whenever any collision is happening. Why? Because the net external force on the system is zero. That means a ball comes, strikes the other ball, right? So in this collision, there is no other force having an influence on these bodies. So the equation we write know that F is equal to dP by dt. Here this F actually means F external. So if this F external or the external force on the system becomes zero, when can this happen? When can you get a differential as zero? Only when this quantity is constant, right? When what is being differentiated is constant, only then you get it as zero. Therefore, during a collision, since the bodies apply forces on each other and there is no external force involved, since there is no external force involved apart from these two bodies, let's say A and B, we always take that momentum is always conserved in any kind of collision. Right? So class, if you have understood, or if your revision of the formulas, the concepts which I've read, which I've expressed on this paper or on this sheet, if this is clear to you all, please raise your hand. Yes, so that we can take some questions. Yes, class. If the formulas and the concepts written on the sheet are clear to you, please raise your hand so that we can move to the questions. Okay, so I can see there's still one person remaining. Okay, Siddharth. Yes, Siddharth, tell me. Okay, Siddharth is also done. Okay. Thank you, class. You can bring your hands down. Have a look. Right? Now, I have given you all some formulas, right? Some superb formulas which are going to help you whenever solving such questions. Just telling you one very quick approach. One very quick approach to solve some problems in elastic and inelastic collision. Elastic and inelastic collision. Right? So let's talk about inelastic collision first. So generally, for your cases in exam, you get questions based on perfectly inelastic collision. Perfectly inelastic collision. What is a perfect inelastic collision? A perfect inelastic collision is the one in which a body comes, let's say A, comes and strikes another body B, right? And both stick together. Both stick together. A and B both stick together and have the same velocity, let's say capital V, after collision. Please write it down, class. Suppose this was U1, suppose this is U2. Both are moving, right? One body comes and sticks with the other body and they move together with the same velocity. They stick and move with same velocity. Please jot it down, class. This is the case of an inelastic collision, right? Now, since momentum is conserved, so let's say the mass of one body was m1, the mass of other body was m2. So I will write m1 u1, that is momentum of first body plus momentum of second body before collision. So I'm see what I'm doing. I'm equating the momentum before and momentum after collision. Have a look. M1 u1 plus m2 u2 is the net momentum of the system before the collision takes place. Correct? Now, what is the net momentum of the system after the collision takes place? See here, the both bodies have sticked together. So they have become one system with mass m1 plus m2. Correct? And what is their net velocity? V, capital V. So this is how we'll relate their expressions of velocities and mass. Class, write it down with you quickly. So when you do this calculation and find out what is the expression of lost kinetic energy, see here, I just told here in the past that here only P is constant, whereas Ke is lost. Some kinetic energy gets lost in case of inelastic collision. So for inelastic collision, the kinetic energy lost or delta Ke loss is given as, class, write it down as m1 m2 m1 m2 whole by 2 m1 plus m2 whole by 2 m1 plus m2 into delta v square. I can also write this as half mu delta v whole square. What is delta v? Delta v is the expression between, or I can basically change it to delta u. See here, I'm doing something, class. I am changing it to delta u whole square. What do I mean? I mean that there is something called as mu, which can be defined as m1 m2 upon m1 plus m2 or reduced mass. This is called as reduced mass. We might come across this concept when we are taking the chapter gravitation or rotational motion, but just for to make things easy for you, we all know that kinetic energy is half mv square, right? On that same basis, you can learn this formula, half mu delta u square, where delta u is the difference between initial velocities before they were about to collide. To express this with an example, have a look, everyone, class. Let's say we have, two bodies, one with velocity 1 meter per second, right, and mass as 1 kg was moving. It sticked with another body on after a collision, which was of the weight again 1 kg, right, and both of them started moving together. This blue body and the black body started moving together with the same velocity v after the collision. You are being asked, you're being told, right, find out the net velocity v of the two bodies after colliding and the loss of kinetic energy in the system, right? What will you do? You will apply first thing. You're being told about the velocity v, right, capital V. How will you find it out? You'll find it out by writing this expression as m1 u1 plus m2 u2 is equal to net mass or the total mass of the two m1 plus m2 times of v, right? We know all the velocities. This body was at rest, second body was at rest initially, so its velocity, initial velocity or u2 is 0. You have u1 is equal to 1 meter per second. Both m1 and m2 are given as 1, so you will have 1 into 1 plus 1 into 0 whole by 1 plus 1. That will give you 1 plus 0 upon 2 or half meter per second, right? Now, how do you calculate loss in kinetic energy? You will have loss in kinetic energy is given as half reduced mass into delta U square, right? This will give you half reduced mass is m1 m2, that is 1 into 1 upon m1 plus m2, that is upon 1 plus 1 into delta U square. Delta U is difference of initial velocities. So one velocity was 1, whereas for the other body it was 0 whole square. So you'll have half into 1 square, that is 1 by 4 joules. So this is how you calculate the loss of kinetic energy, right? Using reduced mass and change in initial or difference in initial velocities. I hope it's clear for everyone. This is reduced mass. Class, please jot this down. If this question is clear, please raise your hand. Yes, class. And this one is difference of initial velocities. Right? Class, please raise your hand if this question is clear. Right. Jot this down, this question with you, and we'll take up the approach for elastic collision. Right? So I hope you all are very well aware what elastic collision is. We just read that elastic collision is a collision in which momentum is conserved always, we know, right? Along with it, we also have kinetic energy conserved, right? So what do some students try to do? They actually try using these two equations to calculate the answer, right? But there is even a quicker approach available, right? What is that approach? The approach goes via the path of understanding what is E. E is called as coefficient of restitution. I'll just write, whenever you are given that elastic collision is taking place, you have to do this thing. Take what for the system, for the two bodies, what is the sum of total initial momentum, that is before collision, right? I'll write it as I, and take the total momentum after collision, right? This is one step. Second step that you have to do is to use the equation of coefficient of restitution. Coefficient of restitution. Coefficient of restitution. Right? I hope you all are aware with this term before. So coefficient of restitution is a very special term which tells you about the ratio of two things. One is relative velocity of approach and the other is relative velocity of separation, right? So yes, class, if you are aware with this concept, please raise your hand. If you are aware with the concept of E, please raise your hand. And also if you have written everything on this page, please raise your hand if you have written everything on this page and if you are aware with the concept of E. Yes, class, I'm waiting. Yes. Please jot this down. Yeah. So basically we have, class, write it down here. Coefficient of restitution is defined as relative velocity of separation, relative velocity of separation upon relative velocity of approach. Right? Now you write this as V2 minus V1, right? Upon, instead of writing U2 minus U1, you will have U1 minus U2, right? This is a very beautiful thing. So you can also write this as minus of V2 minus V1 upon U2 minus U1. Simple as that. Take a minus sign, write it in terms of 2 minus 1, final minus, final upon initial. And the special thing is that for a perfectly inelastic collision, this E value is 0, whereas for a perfectly elastic collision, this E value is 1, right? So your one relation. So see, you have in question, you'll generally have two unknowns, right? You'll have two unknowns. For elastic collision, you're going to use one equation is P initial and P final are equal. See here, I'm telling you the approach. your one approach should be P initial and P final are equal, which is valid for any kind of collision. Second approach should be to take E is equal to 1, right? And for inelastic questions or inelastic collision questions, one approach should always be P initial is equal to P final, right? Most questions will bring this answer. You all already know how to find out the now loss of kinetic energy in an inelastic collision. You can always write E is equal to 0 for a perfectly inelastic collision, right? Some questions are also based on the concept of collision of or conservation of momentum in a particular direction. So let's say I'm giving you all a question. Please jot this down, right? Please jot this down, class. Yeah. So the question is based on the mixed concept, right? You have a wall, you have a wall, right? On this wall, there is a ball which comes and strikes it. There is a ball which comes and strikes it, right? From a given angle. So, just a minute, class. From a given angle. Let's say this is your question from NEET 2016. Write it down here, everyone. You have a ball which comes and strikes a wall at an angle of 60 degrees with the horizontal. Have a look here. Right, at an angle of 60 degrees with the horizontal. The mass of the ball is given as m. It says that it gets reflected without the loss of speed. So if its speed while striking was u, right, while striking was u, with the same speed u, it strikes away in this pattern. So this is how the ball comes, right, with the speed u, and with the same speed it bounces back, right? It is given that it bounces back at a symmetrical angle 60 degrees downwards. You have to find out in the question, right? You have to find out in the question value of impulse imparted by the wall on the ball. Value of impulse. So this was the question asked. How can it be asked in terms of the elastic and inelastic collision? I'll tell you in a short while. First, such the same kind of question, right? Where you have to actually conserve momentum in one of the directions, either X or Y. We'll see that. First, right, you have to find out value of impulse by the wall, on the ball. Yes, class. Solve it. See, it is very simple. We had just read that impulse is nothing but, we represented it by J also, right? Impulse is given as delta P, or m times of final velocity minus initial velocity, correct? Now, how do you actually conserve momentum and in which direction? So this is a very important note, class, right? Note it here. Write this down, note with you. This is going to help you not only in calculating such or answers of such questions, but also in the concept of conservation of momentum in elastic and inelastic collision questions. Have a look. The concept says that momentum changes in a direction only when only where force acts or external force acts, right? Whereas it remains constant, that is momentum remains constant, P is constant in a direction where no force acts, where no force acts. Please write it down. This is very simple. Again, we know that F is equal to dP by dt. So in the direction, let's say we are talking about two directions, right? Fx and Fy. So suppose, and here we have two momentums. One is along x direction, the other is along y direction. So you have to always keep in mind which direction momentum to conserve. So suppose the force along x direction is 0. So then you will take Px is equal to constant, right? If the force along y direction is 0, then you will take Py is equal to constant, right? So class, if this concept is clear to all of you, please raise your hand so that we can do a question on this and log off the class. Yes, class. Right? I am telling you one very simple question, right? Based on this, I'll be giving you all some questions in the assignment, whatever we have read today, and we'll discuss and practice these questions in the evening, right? So, yes, class, here is your question. It says that a ball is moving with speed v. A ball is moving with speed v. Thank you everyone for raising your hands. You can bring them down. You have a ball moving with speed v towards a surface, right? This way. It comes, strikes the surface and bounces back, right? Here, see here, this is the point of bouncing back, and this one is the normal normal to the surface. Here it's how it bounces back along this direction, right? So over here, I'll draw the ball again after the collision, correct? And I'll take its direction as this, right? You are told that the coefficient of restitution is E for the surface. The coefficient of restitution is E for the surface, right? This angle is theta. This angle is theta, right? Suppose its initial velocity, was u, right? Suppose its initial velocity while striking the surface was u. You have to find out what is its velocity while going away, or v. This is such an important question that it is going to help you in 10 such problems of this sort. Just understanding this one question is going to clear your concepts for 10 more such questions. Yes, class, get going. Try yourself first. It is based on the concept which we just discussed right here. Yes, get going. Also, please very vigilant in applying the concepts. Just don't blindly follow it. Yes. Yes. So C class, how will we go about it? I'm writing it here for everyone's convenience. C. So what will happen? Find out the, so here we have the velocity along a particular direction. Find out what will be the velocity along the horizontal and along the vertical. This is u, right? This angle will also be, this angle is theta. So this angle is theta. So this will be alternate angles, interior alternate angles will give you theta. So the vertical component of u will be u cos theta, whereas the horizontal component of u will be u sin theta. Let's do that, correct? Now after collision, let's say velocity is v, correct? So again, how will you find out? We have this vertical and this is the horizontal component, correct? Let's say this angle which it makes with the curve after collision is alpha. How much is it? Alpha, right? So this one will also be alpha. This is v, right? So this angle is alpha, right? See here, because they are again corresponding angles, correct? Since they are corresponding angles, I'll have this is alpha, this is v. So the vertical component of the final velocity will be v cos alpha, correct? And the horizontal component will be v sin alpha, right? I hope I'm clear with this, correct? And we are also given with the value e here, right? So what you'll do, you'll conserve the momentum, right? Let's say first along the horizontal direction. Along the horizontal direction, what you'll write? Along the horizontal direction, there is just u sin theta, right, into mass of this body. Now see, what is happening is this body or the black color ball which is coming and colliding with the ground is actually colliding with the ground, which is so massive mass, has so massive mass that there is almost no change in its velocity. Initially also ground's velocity was zero, finally also ground's velocity is zero. So the momentum of the ground remains zero initially and finally both. Class, I'll repeat. See here, when we used to have two bodies colliding with each other, right? We used to take into account momentum of both, right? Let's say momentum of one was m1 u1 and the momentum was other was m2 u2. But now when you're talking about one body, right, and the ground so the ground has no velocity initially, right? And also when the ball strikes and goes away, we consider that it is able to impart almost nil velocity to the ground, right? So for the ground, u initial and u final both are zero. So suppose ground is the second object, right? So for ground, u2 is always zero, whether you talk about u2 or v2. That is, the final velocity of the ground and the initial velocity of the ground are always zero. So here we have this zero term also, right, which is actually the initial horizontal velocity of ground, which is zero, right? Try to understand this, class, right? Now after understanding this, I'm writing it here. After the collision, body starts moving in the horizontal direction with a velocity v sine alpha. So we'll have this is equal to mv sine alpha, right? Similarly, for the y direction, what will happen? See, for the y direction, what will happen? For the y direction, we will use this formula, this one. And this formula for E is only applicable in the direction of collision. Class, write it down. This formula is only applicable in direction of collision. In the direction of collision. See here. So we'll write in the y direction, E is equal to relative velocity of approach or relative velocity of separation upon relative velocity of approach. See here, this one, separation upon approach. So coincidentally, for our given question, see what is the thing? We have E is equal to v2 minus v1 whole by u2 minus u1, right? This is v, right? v2 minus v1 upon u2 minus u1. The second body is the ground. Let the first body with the ball. So ground has initial with a negative sign. So ground body has initial and final velocities as zero, right? So we will have the expression becoming as minus of v1 by u1, but where? Only along the direction of collision. That is, or basically you can write along the direction in which force is acting, this vertical direction along which the normal reaction is acting. In this direction we will write class the vertical component of final and initial velocities of the ball. So u is u cos theta, u1, v1 is v cos alpha, right? What have I done? I have written, or I have made this collision happen only in the vertical direction, because only in that direction internal forces are acting. That is, the normal reaction is acting only in the direction perpendicular to the ground. That is why I'm taking this expression for E only in the Y direction. Very important, right? Correct? So we have from the given expressions, M and M cancels on both sides. So we'll have M sine U sine theta is equal to V sine alpha. Similarly, we'll have U U cos theta, right? U cos theta into E is equal to V cos alpha. V cos alpha. We have to find out what is V, right? Very simple. Take squares and add. So we'll have U square sine square theta plus E square U square cos square theta is equal to V square sine square alpha plus V square cos square alpha. Therefore, we will have V square times of sine square alpha plus cos square alpha is equal to, right? You can take maybe U square common. So you'll have sine square theta, right? Sine square theta plus E square cos square theta is equal to this expression. Now we know that sine square alpha plus cos square alpha is always 1. So we have final velocity is equal to initial velocity u into under root of sine square theta plus E square cos square theta. Class, if you're clear, please raise your hand. Yes. I'll repeat for all of you. What was happening? A ball was coming and striking the ground, right? It struck the ground and it bounced back. All I've done is applied conservation of momentum for the ball and ground. For the ground, initial and final momentum both are zero because the ground is not moving, and I've applied this equation of E only in the vertical direction, right? You will be doing this thing in almost all the coming questions, right? See here and here and so on and so forth, right? So class, if you have understood these concepts which we have read in today's class, please raise your hands. Yes, class, get going. This is the answer, right? Okay. Atul. Yes, Atul, tell me. Okay, Atul is also clear. Okay, class. So class, let us wind up the class now. We'll catch up today evening, same time, right? And I'll be sending some assignment questions which will be based on these concepts which I have discussed, right? If there is any other concept also for which I give a question, I'll be explaining the same in the class today in the evening. Especially one kind of concept where you have differential and integration involved, which are asked from these chapters, right? Especially work, power, energy, right? So there are several questions from the chapter work, power, energy, where the differential equations are asked, and they are based upon this theorem: work, energy, and work, power, work, energy theorem, right? So we'll take them all up. Thank you, class, for attending this session. Thank you very much, and let us meet today in the evening and discuss some of the assignment questions by tonight. So today, this is how we'll be completing the chapters Newton's laws of motion and work, power, energy. Based on both concepts, I'll be giving some assignments, solve them. Let us meet again by 7:30 in the evening. Anything, anybody who has to ask, yes, feel free. You may ask. Yeah. Anyone? Okay. I think all are clear. Thank you very much, class. Let us meet today in the evening. Thank you.